Hi. So the GATE 2021 exams solutions were officially just released, and what I want to do is I want to go through all of the theory questions across both parts and to try to give a more deep reason for understanding why the solutions are the way they are. So I've never seen these questions before. I don't have the answer solution in front of me. I'm completely doing this live. Well, I'm recording it, but I'm doing it live. So I don't even know where the questions are. So here's part one. So I'm going to look for a theory type question. So that's not, no, that's not a theory question. That's not a theory question. Not a theory question. That doesn't look theory to me. Not theory. Not theory. Maybe there isn't one on this one. Okay, I see regular and context free. Okay, so let's see. So suppose that L1 is regular and L2 is context free. Which of the following is not necessarily context free? So L1 is regular, L2 is context free. So this guy right here is always going to be a context free language. And the reasoning for that is that if you do the product construction with a PDA and a DFA, then the transitions in the corresponding PDA will do whatever the transitions would have done in the PDA. There's another proof that you can do, and I've done it on the channel, which involves context-free grammars, where you can actually make a context-free grammar for the intersection of the two. So context-free grammars are closed under intersection with regular languages. So the answer is not going to be A here. L1 concatenated with L2, this one is going to be a context-free language. And the reasoning for that is, if we have a regular grammar for L1 and a context-free grammar for L2, then what we can do is we can have the new start variable go to S1, S2, where S1 was the original start variable for L1's grammar and S2 for L2's grammar. So it's not going to be B here. It's also not going to be D, because this is always going to be a context-free language, for the same reason that the part B was, where you can do S goes to S1, union S2. And for that same reason, it is context-free. So the answer is going to be C. And the reasoning is that this is equivalent to saying L1 intersection L2 complement. Then what you can do is take L1 to be sigma star. And so sigma star intersection anything is going to be the anything. So then just pick any language where any context-free language where the complement is not context-free. So you could, for example, pick L2 complement being A to the n, B to the n, C to the n, where n is at least 0. The complement of this, of that language, is context-free, but this language itself is not. And so this is not context-free with those choices. So the answer is C for question 1. Let's see. So this one is about asymptotic growth, not really theory type stuff. No, that's not theory. So I don't know much about SLR grammars, but I remember getting asked this question. For any CFG, there's a parser that takes at most n cubed time, and the reasoning for that is that there is something called the CYK algorithm, and it's a dynamic programming algorithm. So I don't know which of the answers it actually is, but B has to be true. I mean, S2 has to be true. So it's one of B or C, but I don't know much about SLR grammars. I need to read up on it. Q6 is not theory. Q7 is not theory, not theory, and not theory. There's time complexity, so it is complexity theory, but not theory of computation. Okay, so let M denote an encoding of an automaton M. Suppose that alphabet 0, 1, which of the following is not recursive? So recursive is another word for saying decidable. It's the same word. So we're just asking which of these is not recursive. So this one is saying we have M's a DFA such that the language is empty, and that is decidable because that's E sub DFA. We just search from the start state, see if we can get to a final state and is equivalent to that question. So the answer is not going to be A. For this one, it's the inverse question. You can just complement the DFA, and if it had sigma star as its language, the complement will have empty, and then we can just defer it to this question, and vice versa if it's not sigma star. So the answer is not B here. For C, this is E sub PDA, and the way that you handle this is a little bit more subtle. You convert to a context-free grammar. Maybe there's a way to do it with a PDA directly, but you convert it to a CFG, and then you figure out whether the start variable is what is called productive. So you figure out for each variable whether they're productive, which means that they actually generate a string at all. And there's a recursive definition for when a variable is productive. Either it makes a string directly, or it has a right-hand side where every variable on the right-hand side is productive. So then we just ask, we just keep adding these variables if we discover new ones to be productive. And if we ever encounter that the start variable is productive, then it can make something. If we can never make the start variable productive, then the language of the grammar is empty. So, which is equivalent to asking whether the PDA's language is empty. So this is decidable. So that means that answer D is not decidable. So this is equivalent to all sub CFG. And then the way to show that that's undecidable is that you can encode, in a sense, the computation of a Turing machine, or at least all the strings that don't represent a Turing machine running on an input. And you can have that the language of you can design a machine such that it doesn't accept sigma star exactly when the Turing machine accepts W. So this is equivalent to asking whether a Turing machine accepts a string, which is an undecidable question. So the answer is D here. 13 is not theory, not theory, not theory. Planar graphs, nice. But not theory, not theory, not theory. I don't see theory, no theory. Okay, so I have a grammar here, but that doesn't look to be like truly theory of computation type stuff. Not theory, that's Boolean algebra stuff. Not theory, not theory, not theory. There's a lot of questions in the first part. Okay, so we have something that's based on LL parsing, and I don't know much about that, at least right now. So we got a bunch of relation type stuff. Let's see. Okay, so here's a theory one. So here we have a language where we have all strings that ends with the substring 0, 1, 1. So it ends in 0, 1, 1. And it looks like we're asking which of these accepts the language. So let's see. So it might actually help to actually make the machine first. So what we can do is we can make a start state, and we just encode the last 3 characters. And here in this final state, if we see a 1, that means we really ended in 0, 1, 1, 1, which means we didn't really end correctly. So what we need to do then is to go back to the beginning, I think. Yeah, because if we see a 1 here, then the 0 needed to be at the third to last character, which is not anymore. So effectively, we have to start over. So the 1 would have to go here. So that means that that I think the answer should be D here. I think it should be D, because that's the only one where the 1 transition actually goes back to the start state. And you need 4 states, so each one of these is minimal. So it's not like there could be some other way of doing the DFA here. Yeah, I'm going to go with D here. So now another one. Turing machine M. Consider the following 2 languages. So we got a machine where M takes more than a certain number of steps on all inputs versus on some input. So which of the following is correct? So is whether each one of these is decidable or not. Okay, I think I would say that L1 is decidable. But let me actually think through this. So if we have a tape right here, we will never, for a particular input, we will never have to go more than the 21st character. And the reasoning for this is that if the machine ran, if we needed to access some thing past this point right here, then that means that we took more than 2021 steps. So that means, for all intents and purposes, we only need to look at the first 2021 characters, because we will never inspect any character past this point if we cut the computation off at 2021 steps. We may stay down here further, but we can never go past this point right here. So that means here, for... Oh no, it's more than 2021. So if it takes more than 2021, then... Okay, that's interesting. So if it's on some input... Yeah, so the main concern is, what is the difference between all and some here? Oh, actually, no, that's okay. So if we can actually just simulate all strings of length at most 2021 and run them for 2022 steps. Okay, so yeah, so that's the trick. So in both cases, what we should do is run all strings of length at most at most 2021 for 2022 steps at most. And if it stops earlier, then that's okay. So then what we do is, if any string took more than 2022 steps, if any string took longer than this or longer, then for the answer for some input is going to be yes, because that meant that some input took at least this length. And then for the all inputs one, if you just check if all of these took more than 2022 steps, then that means any input that's longer than this right here, we're not going to be able to look at all of those cells anyway. So we would only need to look at the first 2021 characters, assuming the length is at most 2021. If it's longer, then we don't really care, because we will never see those cells for the purposes of figuring out whether strings will take that long to get there anyway. So, in fact, both of these are decidable, purely because we can just do a brute force search by limiting the amount of time that we need to spend on each of the inputs. There's only a finite number of strings of length at most a certain number, and we're running each one of them for a certain number of iterations. And so therefore both of these are decidable for slightly different reasons, but based on the same concept that we can just brute force search all the finitely many strings that we ever need to consider. So that's not theory, not theory, not theory, not theory, not theory. Got some pseudocode, hashing. You all have to learn a lot for this test, it looks like. Okay, so we got a PDA right here. So we got transitions that look like this, standard stuff. So that's just another way of saying the same thing. Consider the following PDA. The number of strings accepted by the above pushdown automaton is what? Okay, so we are going to have a pound sign on the stack to start with. That's how we start out. Then we're going to have some number of A's, capital A's I mean, on the stack. And then non-deterministically read B's. And then that means here we're going to be popping off some of them. And then that means that we need to have at least one occurrence of A on the stack to get to Q3. If we have more, then that's okay. So I think this language is this. It's going to be A to the I, B to the J, because little a's have to come first, b's have to come second, where I is bigger than J, I think. I think that's it. Because we need to have at least one more occurrence of little a compared to B. Yeah, at least one more. So then now we just need to figure out what is the number of strings that fulfill this criteria. So that means, okay, so it's length 100. So then now what we need to figure out is what is the sum over I and J such that I plus J is equal to 100 of 1. We're just adding up all the possibilities from I and J from actually, do they need to be at least 1? J has to be at least 0. So that means I has to be at least 1 according to the condition here. And actually, we need to condition on the fact that I is bigger than J, but that's less of an issue. Okay. So then how do we actually calculate this? So we would need to have... So let's go from I equal to 1 until what's the largest value of I it could be? It could be 100, because J could be 0. And then J from 0 until I minus 1. I think that's okay. So then, of 1. So we're counting 1 for each one of these J possibilities and then add them up for all I. So we'll have I equal 1 to 100 of, well, this is just I. Yes, that's just I. And then adding 1 to 100 is equal to actually I should say, not this way. I should say n times n plus 1 over 2 is just adding from 1 to a certain number, which is n. And in this case, it happens to be 5050. You can see that I haven't rehearsed this because I'm doing it live. Adding from 1 to 100, I know that sum already, but you can actually put 100 times 101 divided by 2 and you'll get the same thing. So the number of strings is 5050. Unless I'm made a slight mistake here. All right, so no theory here, no theory, no theory. Okay, so that's the first part. Now let's do the second part. So no theory, no theory. Goodness, there's a lot of questions in this part. Listening to music. Oh, that's interesting. No theory, no theory. Got unweighted graphs, heaps, C program. Floating point, oh god. Multiplexers? Yeah, so no theory here. Binary search. Oh, okay. So, I don't know why I moved there. Okay, so let L be an arbitrary regular language accepted by a minimal DFA with K states, okay? So the L can be, has a DFA with K states and no smaller. Which of the following languages must be accepted by a minimal DFA with K states? Okay, I think, so this one should be okay. Purely because this is just the complement operation, because the alphabets are the same. And for DFAs, you can just complement which states are final and not final, and you can get the complement. So you're not adding additional states. And if you can do it smaller, if you can make the complement DFA smaller, then what you can do is just complement it back, and then you just contradicted the fact that there's a DFA that's minimal with K states. So in fact, I think C should be the answer here. For A, okay, yeah, so for A and B, I think if you had K equal to 1, then for these two, you need to have at least 2 states. Actually, at least 3 states, I think. Yeah, to get the 0 and 1, you must have at least 3 states here. So that means that for these ones, you need at least 3 states, but the DFA for L had 1 state. So, so these are not right. And then this one is not right because if you had a single string in here in L, then to get the one for LL, you need to have twice as many states as you did before. And that's pretty easy to see because, like, for example, if L was just a single character A, then LL, which is what this concatenation is AA, then you need 2 states for this guy, which is fine, but then you need 3 for this one. So maybe not twice as much, but it's roughly twice as much. Maybe minus a little bit, but it's effectively twice as much. So the answer for this question is C. Let's see. So we have functions. Okay, let L1 be a regular language and L2 context-free. Which of the following is our context-free? So this one, we actually just went over this. So this one is not going to be right because if we let L1 to be sigma star, L2 to be any context-free language, which its complement is not context-free, then this guy is not context-free. This one is equal to L1 intersection L2, and we saw that before that this is context-free because we can do a product construction between a PDA and a DFA. So this one is okay, so that one's okay. So I'm going to circle that. This one, let's rewrite this. So let's L1 union, okay, so L2 union L2 complement is sigma star. And anything union sigma star is sigma star. And so sigma star is regular and then hence context free. So C is also an answer. This one, okay, so we may have to do this in parts. So this part we saw before that that's a context free language. And then this one is also a context free language because regular languages are closed under a complement. And we're unioning them together. So a CFL union a CFL is also a CFL. So I would say all 3 of these is correct. So A is not correct here. Compilers, CPU, propositional logic. Okay. Continuous functions. So that's a code, that's not the same thing. Caches, circuits. Wait, was that one? No, that's probability. C code, scheduling type things, programs. Okay, regular languages. So every infinite regular language contains an undecidable language as a subset. So and the second one is true. Every finite language is regular. So every regular language contains an undecidable language as a subset. I remember. I think that's also true. Let me think about it. So every infinite regular language contains an. Yeah, it is. So this one's actually kind of cool, and I may do a video on it in the future. So if the regular language is infinite, then in the DFA, what we can... So this is actually quite complicated, but it's kind of cool. So what we have is something that looks like this, based off of the pumping lemma. So we have a way to break up the string into those famous 3 parts, and yada, yada, yada. So we saw, if we label these x, y, and z, the x, y to the I, z is in L for all I. For all I at least 0. So what we are going to do now is look at this language. So I'm going to call it U, which is 1 to the I, such that I encodes an instance of ATM. So it's the unary encoding of some instance of the undecidable problem ATM. Then what we can talk about is, well, this is an undecidable set, because because what we can do is we can just extract the length of this, encode it as the machine and the input, and now we can solve ATM if it were decidable. So what we can do here is we can talk about the subset of L, which I'm going to call S, such that S is equal to x, y to the I, z, such that I is in U. So each one of these strings is in L, so therefore this is just a subset of the integers, namely the non-negative integers. And so this S right here is a subset of L, but it's an undecidable subset. Because what we can do is we can just extract the Y piece, and we can then figure out, we can get the number of times Y occurred, and then now we effectively have the same thing as U here, and which is also undecidable. So every infinite regular language has an undecidable language as a subset. So the answer to this one, both of them are true. That's a cool problem. I really like that problem. Okay, so master theorem, dependencies. Okay, so for a string W, to find the reverse of that way, yep. So which of the following is our context-free? So this one is context-free because we can have the start variable make A, B. So A and B are variables. A will make the first piece, which is just palindromes, and B will make the other palindromes. And the W and X have nothing to do with each other, which is good. So D is also context-free, because what we can do is have S go to A, where A makes the palindromes, the W palindromes, or B, where B makes the X palindromes. And there's no correlation between the W and the X here, so therefore we are good there. So for this one, so A is not context-free. And the reasoning is that if we pick the string W, oh, not W here, maybe I should give it a different name. So let's call it Z, which is 0 to the P, 1 to the P, 0 to the P, 1 to the P. Then each of the W pieces and the X pieces are separated by a long string, and by the pumping lemma for context-free languages, we can't hit the zeros at the same time or the ones at the same time. So that one's not context-free. C is context-free. So why is this one context-free? Well, maybe I'll go down here. So what we can do is we can have S make the W palindromes, or A, the variable A, which makes anything. And the reasoning for that is, well, the X piece doesn't have any dependency whatsoever, so it can be technically anything. In fact, this language, I just realized, is equal to sigma star. And why is that? Well, just let W be the empty string, and then X is just any string now. So now I can make any string. So C is sigma star, and hence is regular, therefore is context-free. So all three of these are context-free. And A right here is not context-free. Okay. Multi-threading code. Let's see. Some algorithm stuff, directed graphs. Okay, so which of the following regular expressions represents the set of all binary numbers divisible by 3? Assume that the empty string is divisible by 3. So let's just make sure that, yeah, so all of them do make the empty string, which is good. Okay, so let's see. So I have a feeling that it's going to be B and D, but I'm not sure. Well, so let's see. All binary numbers divisible by 3. We've made this DFA many times on the channel. So Q0 is going to be the accept state. And what we do is we look at the binary representation, and 0 represents multiplying the number by 2. 1 being red means multiply the number by 2 and add 1. So then we just keep track of what the remainder is over time. And we've done this many times on the channel. And then 2 would go to 1, and then 2 would go to itself. So effectively, we have, so the language of this guy is 0 or I'll do it in plus notation. So plus, okay. Actually, I'm just gonna do a slight cheat, which is to simplify this. So this is 0, 0. Actually, no, 0, 1, star 0. So then it would be 0 plus 1, 0, 1, star 0. That part starred with a 1 after it, and then the whole thing starred. So do we have this one? Okay, so yeah, so A is right. So A is obviously identical to this. So what about these two? These three, I should say. Can I get a single one? So C is equivalent to A. And the reasoning is that when you have something plus something and then the whole thing is starred, it turns out that you can just put a star on each of the two pieces, remove the plus, and then those are equivalent to each other, purely because of the outer star here. So C is correct. What about those two, though? So what is this really saying? So this is saying we can have... yeah, what is this actually saying? So what is the difference between these two? So this one has a 1, 0 here versus a 1, 1. This has a 0, 1 versus a 0, 0. So that's 3. Okay, yeah, so this D won't work. Or at least I don't see how, I don't think it works. So what we can do is focus on this piece right here. And what we can generate is the string 1, 1, 1, 0, 0, I think. I think this will work. So this first piece is 7 times 2 times 2 is 28, which is not a multiple of 3. Because the 1, 1 is generated by this 1, 1 at the beginning. This single one is from here, and the 2 zeros are for the last 2 here. We don't have to go through again, so we can make that string, which is not a multiple of 3. I presume we can do something similar here. So I'm just trying something. So let's say we do 1, 0, 1, but that's 6. Okay, yeah, I think we can do this. So let's see, what is this? So this is 1, 2, 4, 8, 16. So 16, 8, no, 16, 4, 1. So that is 21. Can I make that string? Yeah, I can make that string. So this is not a oh no, it is a multiple of 3. Oh my god. I can't believe I forgot 21's a multiple of 3. But I think we can repeat this. So if I do 1, 1 in here, so this is 8 plus 2 plus 1, so that's 11. And then what about 0, 1 on the outside? So that'd be 22 for this first part. Oh, that'd be 45. So maybe this one does work. Is there a reason why it wouldn't? So the 0, 0 won't help us. That's multiplying by 4. So it'd have to be some number of 1s. If this doesn't work, actually. Times... Yeah, so these 1, 1s and the 0 won't help us. Because if I apply a 1, 1 at the end, that corresponds to multiplying the number by 4 and adding 3. So So, and then it would have to have been not a multiple of 3 to start with. The zeros don't help either because they just multiply the number by 2. So you would have to have started with something that is not a multiple of 3 to start with. So let's see, could this possibly not work? So if this is not the right regex, it would have to be because of this culprit. So why would this not work? So the 0, 1 says that this is always odd for that part. So odd, either timesing by 4 or timesing by 2 and adding 1. So let's see. So we have the base case of this is 1, 0, 0, 1, which is 9. The 0 zeros are being inserted in here, so that's being multiplied by 4, so that doesn't help. What does the 1 do? So what does 1, 0, what does sticking a 1 in here do? Let's think. So for the number at the beginning, which is 2, you're multiplying by 2 and adding 1. I have an inkling that this is going to work. Is there something from the picture? Maybe let's go back to the DFA, that might help. And let's blow it back up to what it had before. So this is what we had before. So then in terms of the DFA's perspective, the 0 here is just a self loop. The 1, 1 is going back and forth. 1, 0, 1, 0, 0. Okay, yeah, this will work. This answer's right. So it helps to look at the DFA here. So here's the reasoning. So the 0 at the beginning, because of the star, we can do any one of these as many times as we want. So we can do the 0 as much times as we want. We can do the 1, 1 as many times as we want, which from Q0 ends up back to where we started. Though this part right here is saying the 1, 0 ends up at Q2. So at this parenthesis, we're at Q2. The 1 we can do as many times as we want. We stay at Q2. The 0, 0 goes back to Q2. So at the end of this parenthesis right here, we're still at Q2, and this 0, 1 will take us back. Maybe this is the reason why this one didn't work. So these two parts are okay. The 1, 1 gets us back to Q0. The 1 will take us to Q1, 2, 0, 0, 0, 0. So this will end up at Q1. So that's why this one didn't work. That's why this one worked. So the answer to 47 is A, B, and C. That was a nice problem. It made me actually think about this. Well, actually, I had to think about all of them, but it made me think a little harder. And that's it. So hopefully this was interesting. Leave comments about any of these gate questions down into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.